Ok, bah, je propose qu'on qu'on commence et on verra s'il y a plus de gens qui se joignent. Comme je disais tout à l'heure, pour ceux qui n'étaient pas encore là, malheureusement, aujourd'hui, c'est la semaine de la CF2A. Je n'avais pas remarqué au moment où on a fait le calendrier. Donc voilà, je m'excuse pour le- la possible faible attendance, audience dans le séminaire. Aujourd'hui, donc, on a le plaisir, merci beaucoup, Joana, de venir nous parler détection dans les cubes, dans les données hyperspectrales. On ne se connaît pas très bien, je fais juste une petite introduction. Tu complètes, hein, tu es au CEA actuellement, dans le labo de Cosmostat, et puis tu enseignes aussi pas mal pour les méthodes de machine learning appliquées au traitement du signal, c'est ça?
Tout à fait.
Très bien. Eh bien, écoute, merci beaucoup encore d'être là avec nous. Je te cède la parole. Tu peux y aller. Merci beaucoup.
Ok, merci. I'll switch to English if that's all right.
Yes, of course.
That's fine. Okay. So I would like to start by thanking the organizers for having invited me to give this talk. So today I will speak about robust anomaly detection for hyperspectral imaging. So as you mentioned, I am currently working at Cosmostat. So most of my work is actually on machine learning for astrophysics. But I decided to present this today on hyperspectral target detection, even if it's remote sensing, because I think it would be interesting application, radioastronomy, for these methods, and I think it should get it's worth to be studied. So, I'll start with hyperspectral imaging, even if most of you probably know. So it stems from the fact that for a given material, the amount of radiation changes with wavelength. So usually in remote sensing, the amount of sunlight that has been reflected on the ground is remotely measured by a spectrometer at the large number of narrow contiguous bands. So this will allow to create a spectrum for each material, and this variety of spectrum will allow to tackle some different tasks. Some of the different tasks that are especially studied in hyperspectral imaging include target detection and change detection. So my talk today will be mainly focused on this. But there are also important tasks like determining which kind of materials are composed in the image, because usually in the image we don't have just one material, but a mix. So determining which are the different components of the image is what's called a mixing, and also classical classification task, in which one would like to decide if a pixel belongs to a certain material or not in a supervised way. So as you said, today I'll be focused mostly in target detection. There are two main methods in target detection for hyperspectral imaging. Either one knows the spectral signature of the target that we're looking for, and if you know the spectral signature, you can use it as a steering vector in classical target detection methods. In other problems, we have no idea how is the target. We don't have any information available on how the target's gonna be, and we just search to detect anything that is different from the background. It's why it's called anomaly detection. So most of these methods are also found in signal processing, notably in radar detection community. So most of the target detection methods that are studied in hyperspectral imaging include the match filter and its adaptive version, the ACE detector, superspace detectors, etc., etc. But most of the methods come from classical detection theory. Again, most of these techniques rely on the fact that our data are Gaussian, so we derive detectors, anomaly detectors, and target detection, assuming that our data is Gaussian. Common assumption that people also do is to say that our data is especially homogeneous, meaning that we don't have very different materials, and then we can just assume that it's homogeneous all through the image. So what we usually do is we parameterize the Gaussian distribution with its first and second order moments, namely the mean vector and the covariance matrix, and we use them in the detection schemes. So in most of the cases, we'll end up needing to estimate these values from our images. So we'll need to estimate both the covariance matrix and the mean vector. So that was just a brief introduction on what problems I'll be speaking about today. In the following, I'll start with some preliminary notions on detection theory. Then I'll present the non-Gaussian framework. Namely, I will speak about elliptical distributions and the corresponding estimates that we're going to use in this framework. Then I'm going to show how we can use these elliptical distributions and robust estimates for anomaly detection. And then I'll end up with some conclusion and perspectives. The problem is the classical problem in target detection. What we want to do is, from an observation vector X, the problem that we're searching to resolve is to decide if a signal S is present when it's corrupted by an additive noise B. So this problem can be formulated as a classical binary hypothesis test. And in a classical binary hypothesis test, what we do is, for the observation vector, if it contains only noise, will be an hypothesis 0 or null hypothesis. And in the alternative hypothesis, the target is present with the additive noise. Besides this observation vector X, we'll assume that n signal-free independent observations are available. They're also referred to as the secondary data, in order to estimate the background parameters, the parameters that will characterize the noise. I insist on the fact that we usually assume that this n secondary data only contain noise, and there's no target or signal supposed to be in the secondary data. So in hypothesis testing, what we usually do is we use the Neyman-Pearson theorem in order to maximize the probability of detection for a given fault alarm probability. So for the Neyman-Pearson theorem, what we do is, firstly, we start building the likelihood ratio. In order to build the likelihood ratio, we assume a certain probability density function for the hypothesis 1, and we divide it by an assumed probability density function for the hypothesis 0. So we create this ratio, and when we compare it to a threshold. If it's larger than this threshold, we'll decide that our target is present. And if it's smaller than the threshold, we'll decide that the target is absent. If we decide that the target is present when there's actually nothing, we make a mistake. It's what it's usually called a false alarm. On a first stage, we want to make sure that this kind of mistakes, these false alarm mistakes, don't grow too much. So we want to set a value of the false alarm that has to be guaranteed for our statistic test. Then in the second stage, you're going to maximize the quality of detection in order to weigh the performance under the hypothesis 1. So this is the kind of setting. Moreover, we usually assume the Gaussian distribution. So as you probably know, an m-dimensional vector X has a complex Gaussian distribution. If it's probability density function, if it exists, it takes this shape here, where mu is the mean vector and sigma is the covariance matrix. So once we have the Gaussian distribution, we can easily derive the maximum likelihood estimate. So in the case of Gaussian distributions, the maximum likelihood estimators are the well-known sample mean vector or covariance matrix. So on the left, I showed the sample mean vector. It's just the classical empirical mean. And on the right, I showed the sample covariance matrix. So those are the most widely spread and widely used estimators for both the mean vector and the covariance matrix, because they are very easy to implement. Their analysis it's simple, and they have very good and well-known statistical properties. So they are consistent, unbiased, and efficient. We also know their distribution. For the sample mean vector, we know that it's distributed as a Gaussian distribution, and the sample covariance matrix follows a Wisher distribution. So we're going to be using this in the non-Gaussian framework in the following. Before, let me show how do we do for selecting our N secondary data. So on our hyperspectral image, what we're going to do is we're going to use a sliding window that's going to be centered on the vector under test X. I'm going to take the surrounding of this vector and use it as a secondary data. So our sliding window can be a rectangle, can be a square, as you wish. And we're going to just move it through the image. So the size of the window has to be large enough in order to the covariance switch to be invertible, and it has to be small enough in order for the patch that we've taken with this mask to be homogeneous enough spatially. Two important statistical assumptions that we do for the secondary data is that the pixels that are in the mask are statistically independent, meaning that they are spatially independent, which sometimes is not the case, but so far we're going to assume this. And we're going to also assume that the pixels in the mask follow the same distribution, that they are identically distributed. So let me now move to the non-Gaussian framework. I just presented the Gaussian distribution. However, hyperspectral data are generally non-Gaussian. Usually they present a special heterogeneity in the intensity. Sometimes we have peaks in some places that we usually don't have in Gaussian distribution, so it's rather heterogeneous. And we cannot use only the Gaussian distribution to describe them. One example of this it can be seen in this figure. So on the left side, we plot a quadratic form that should be following a chi-squared or cotangent square if the data were completely Gaussian. But as we see that its statistical behavior diverges from the Gaussian, we can conclude that the data are not completely Gaussian. Moreover, on the right, we showed the cuckoo plot on some hyperspectral data, and we also see that they divert from the expected behavior in Gaussian case. So that's why elliptical distributions were introduced in order to model hyperspectral imaging. Even if elliptical distributions have been largely studied in hyperspectral community, people usually use Gaussian estimates for the reasons I said, because they are simple and statistically well characterized. So what are the elliptical distributions? I'll present you here the probability density function. So it takes this form here in red. I want to take your attention to the fact that it almost looks like a Gaussian distribution. So it's not an exponential anymore, it's the density generator, Hn, and this H can be anything. So this equation here follows a probability density function. That is that it's positive and the interval is equal to 1. So we have some normalization as well to make the interval equal to 1. Here mu is the mean vector and sigma is the scatter matrix. So the scatter matrix is equal to the covariance matrix up to scalar constant. So the thing is that the covariance matrix is not always defined, but the scatter matrix is always defined. So on the bottom, we displayed some examples for elliptical distribution. So in black, we have a Gaussian distribution, which is a particular case of these elliptical distributions. And in gray, in blue, and red, etc., other distributions that have heavier tails than the Gaussian one. So some of the advantages of this model is that it's more general. It has very powerful capacities. So it stands in the first place the Gaussian model. It includes the K distribution, the Weibull distribution, Cauchy, generalized Gaussian, student distributions, etc. It also includes the Gaussian model. So you take into account the Gaussian model if you use this kind of distribution. it allows us to model the heterogeneity of the background that I mentioned that it was present in the hyperspectral imaging. So all these textures that we can see in the image are taken into account by using these kind of models. And we can consider the possible correlation existing within the different spectral bands with the scatter matrix. So in the case of the density generator H being perfectly known, one could easily derive the maximum likelihood estimate. However, this is rarely the case. Usually we don't know the perfect distribution of our data, just the model that we have assumed. So if we don't know it exactly, we're going to use something that is robust. And that's why we propose to use the M estimators in this case. So the M estimators are defined as the joint solution of these two equations here. So we have an equation mu n for the location estimator and sigma n for the scatter estimator. So we have kind of pondering weighting functions u1 and u2 that weight the classical estimate, and these weighting functions, they act on this quadratic form here. So u1 and u2 act on this quadratic form, and this quadratic form serves to evaluate if our data is outlying or not. It's very different from our distribution or not. So if the data resemble to our distribution, they will be kept. And if the secondary data are very impulsive, very different from our distribution, they will be attenuated. So different choices of U1 and U2 will lead to different kinds of M estimators. I will show you some examples next. And the existence and uniqueness of the solution of these equations have been proven, provided some conditions on U1 and U2. That this was derived in 76 by Marona, and extended to a complex case by Olivia. And they were originally proposed, these M estimators, as a generalization of the maximum likelihood in the elliptical distribution case. So they can be seen as a generalization of the maximum likelihood for the elliptical distribution. So here I present some examples on the weighting functions. So on the right, on the left now, so with the sample covariance matrix. So the weighting functions is completely flat. So it's naturally a non-robust estimator. On the right, we have Tyler fixed point estimator, where the weighting function is m over the quadratic form, m over t. So the samples that are very outlying will be strongly attenuated, and those that are not outlying will be augmented. And Huber's M estimated this kind of mix between both of them. So for samples that are very outlying, that are very different from the mean, for instance, those that we can see this impulsive distribution here, those that are very, very different will be strongly attenuated. And those that are very similar to the background will be kept. And then this K is a parameter that you can test. More specifically, the fixed point estimators, also called the Tyler estimators, are found by solving these two fixed point equations. So we have these 2 point equations, and we need to use an iterative algorithm in order to find the solution for this. Remark that they are weighting the mean, and they are weighting the covariance matrix. So this weighting, as I mentioned, it stands on how outlying the secondary data are. So this estimator, one of the most remarkable properties of this estimator is that it doesn't depend on the underlying elliptical distribution. Its behavior is the same independently on the distribution. It's robust to outliers, to strong targets or scatterers in the secondary cells. We also know its statistical properties. It's consistent, unbiased, and it's asymptotically Gaussian. So it behaves asymptotically as a sample covariance matrix. So it's a Wisher distribution with m+1 over n degrees of freedom. So we lose a tiny bit on the efficiency, but we gain in robustness. For the Huber M estimator, here I present the two weighting functions I showed the drawing before. So we have this U1 and U2, and we have to find the K that we want to choose to adjust the behavior of Huber M estimator. So for values of the quadratic form Ti that are very high, very outlying samples, they will fall outside the interval and they will be attenuated, as it's commonly done for the fixed point. And for normal values, for Gaussian values below the threshold K squared, they will be kept, uniformly kept, as we usually do with the sample covariance matrix. So the parameter K can be adjusted in order to choose the percentage of data that you want to be treated as a Gaussian. Again, is consistent and unbiased, and it's asymptotically Gaussian as well, with nu1 n degrees of freedom, and nu1 is well characterized and it's very close to 1. So again, we lose a little bit in efficiency, but we gain in robustness as a counterpart. So now, what I will present is I want to present these estimators for the case of anomaly detection, in case of target detection in hyperspectral imaging. So as I mentioned at the beginning of the talk, anomaly detection is to detect anything that is different from the background. So we don't have any information about what are the targets that we're looking for. We just seek anything that is different from our surroundings. One of the drawbacks of these approaches is that we cannot actually distinguish between the two targets and the detection of only bright pixels on the background. It's very complicated to evaluate this kind of methods, but it's also the case commonly in unsupervised learning methods. We don't have background truth, so we're not sure about how are the performance of the method. So firstly, for the derivation of the detector, what we've done is we created the likelihood ratio test that I presented at the beginning, and we derive it following Kelly's hypothesis with respect to a steering vector P, with respect to the spectral signature. So if we derive with respect to spectral signature, we get this expression here, this quadratic form here, where mu is the sample mean vector and sigma is the sample covariance matrix. So this corresponds also to the Mahler-Anomaly distance. So what we do for anomaly detection, and this is the most classical way of doing it, is we center ourselves in a pixel, we take the surrounding pixels as secondary data, and we use the secondary data to estimate the sample mean vector and the sample covariance matrix. If our data are actually Gaussian, this square form, we know how to characterize it. We know the distribution of this square form. So if both are estimates and under the Gaussian distribution, this is a non-central F distribution and a hypergeometric distribution with m and n minus m degrees of freedom. And of course, when n tends to infinity, the distribution tends to a chi-squared. So this relationship that allows us to settle the threshold, to know how it's going to behave under null hypothesis, has been tested on first simulation called the Monte Carlo simulation. So we plot the theoretical lines every time and estimate and the ones with the unknown parameters, sorry. And on the right, what we've done is from a real hyperspectral image, we took a patch that is Gaussian. It corresponds to a region where there's only water. So that region was very homogeneous, and we fit that data to our theoretical threshold. So this is nice because this allows us to decide on the threshold, and this threshold will give us a fixed probability of false alarm. However, most of the time our data is not Gaussian. So instead of using the sample mean vector and the sample covariance matrix, what we could do is we could build the detector with the M estimators instead. So we can replace mu and sigma for robust M estimators or shrinkage estimators instead of using the Gaussian ones. However, if you're in non-Gaussian approach in the elliptical distributions framework, this quadratic form will depend on the underlying non-Gaussian distribution. So the distribution will depend on what's the actual on the actual data. Meaning that if you have Gaussian, it will behave like this. If you have student, it will behave like this, and so on. So we don't have a unique distribution for this. Let me show you some results for images, for a hyperspectral image. So this is a forest region that's highly non-Gaussian. And in this forest region, we have artificially put some targets. And on the left, I showed the position and the shape of the different targets. And on the right, I showed the spectrum of this target. So the target spectrum corresponds to this panel tissue, and this panel tissue spectra has been artificially plotted in a hyperspectral image. So now show some results on this HiMap image. So on the top row, I showed the results with sample covariance metrics. In the bottom, I showed the results with the fixed point estimates. So the sample covariance and all the images, sorry, are all displayed in the same false alarm values. So on the top row, we see that sample covariance metrics can only detect 1 pixel targets, and also in the case that there is no other target next to it, because otherwise, if you have targets next to it, it will corrompt the estimation and you won't be able to detect it. While fixed point, it's robust to the presence of targets in the secondary data. So if the targets are contained in the secondary data, it will attenuate them, and then it will be able to find them in the detector. So something that a modification from this is that I realized that most of the targets that we were detecting were very bright. So if you have something that is very bright, it's very easy to detect, very easy to spot. But if we have fainter targets, something that is embedded in the noise, we couldn't find it with anomaly detection. It was surprising because if you have hyperspectral data, with the shape of the spectra, we could take advantage of this variety in order to detect faint targets. So what we did is we started from the stochastic representation of elliptical distribution. So elliptical distributions X can be written according to its stochastic representation, sorry, like this. So they are defined as a mean vector mu plus random uniform random vector that is distributed on the sphere U, multiplied by a matrix A. A is obtained as a factorization of sigma, and multiplied by a generating variate R. So this R contains information on the generative function H that I showed you before. A contains the information on sigma, on the scatter, and U is just a random variable on the sphere. So this is useful if you want to generate elliptical distributions. So in order to get rid of the energy of the signal, what we propose is to project this X onto the unit hemisphere. So we project our random vector in the unit hemisphere for center data. What we get are the so-called angular Gaussian distribution. So for the central case, or in case we know mu, what we can do is like by definition, so we remove mu, and what we're gonna have is that it's generating variate times the factorization of sigma times the random variable on the sphere. So this will almost surely become independent of the generating variate, which means that if we have the same factorization of our scatter matrix sigma, but we have different distributions. For instance, we have a Gaussian distribution or a K distribution or a Cauchy distribution, they will end up being the same on the hypersphere. That's why we call it anomaly detection on the sphere. So this angular Gaussian distribution, they're usually called the angular Gaussian, even if your underlying elliptical distribution is not Gaussian, all of them end up with the same probability density function. So if it exists, it takes this formula here. So what we do is from the center vector, we normalize it, we project it on the M hypersphere. And this model allows us to still take into account the heterogeneity and the non-Gaussianity of the data. The matrix sigma is also the scatter of the distribution that also models the spectral correlation between the different bands. However, these angular Gaussian distributions, they don't admit the stochastic representation that the elliptical distribution do, but we won't be using it. In the case of angular Gaussian distribution, the fact is that we can derive the maximum likelihood of the shape matrix and get something that looks like this. So this, it's more than similar, it corresponds to Tyler's estimate. It corresponds to the fixed point estimate that I presented in the M estimator. So of course it's consistent and unbiased and synthetically Gaussian. As before, and it doesn't depend on the true distribution, on the true underlying distribution, and it's robust. In this case, it's besides being the maximum likelihood, it's robust to the presence of outliers or highly impulsive samples in the reference cell. In the case of positive data, if the location vector, if the mean vector is unknown, we'll need to estimate it from the data sample. And usually what we do for angular Gaussian is we just use the Tyler mean vector estimate as well. So we can robustly estimate both the scatter metrics and the mean vector with both estimates. The resulting KGD won't be unaffected anymore by the underlying generate variate R, but it's still interesting. What we can do now is we can derive, as before, from the angular Gaussian distribution, the likelihood ratio test with respect to the steering vector as the case for the elliptical case. So we derive it with respect to the steering vector, we'll get something like this. It's very similar as what we had before. However, in this case, S is an angular Gaussian distribution, which is independent of the true elliptical distribution. And sigma ML won't depend neither of the underlying true distribution, which makes that this quadratic form that still corresponds to the anomaly distance won't depend on the heterogeneity of our underlying data. So whatever underlying statistical distribution we have, if we project it on the sphere and we use this as a texture, we'll have the same distribution for these statistics. So we've shown that in some simulations. So we've seen that the behavior of this statistic test is the same independently of the distribution. So we've done it for Gaussian distribution, but also for K-distributed data. So for K-distributed data with different degrees of impulsivity. So we saw that the behavior is exactly the same, which is it's a very nice property. It's why it's called CFAR, so constant false alarm ratio detector. And we also checked on real hyperspectral data how was that behaving for faint targets. So we also plucked artificial targets on another image. So here there are, I don't know if you can see it correctly, but there are 3 rows. The first row are very faint, and the second and the third row are more and most powerful targets. So the anomalies that we plucked, the artificial targets that we see here, correspond to this target spectra here. This target spectra is very similar to the water.
think we've lost you.
Results that when we're closer to what we are in this last case, vous m'entendez ou pas?
Ça y est, c'est mieux. Il y a eu
Désolé.
Je suis seul, mais il y a eu une petite coupure là.
Vous voulez que je...
Maybe the last slide, yes, the slide before.
Désolé, c'est coupé. Vous m'entendez?
Oui, ça y est, on t'entend bien là.
Désolé, hein, j'ai des petits problèmes de connexion. Okay, so as I was saying, show the last result on a real hyperspectral image. So on the left, I show the results for classical methods, how we usually do anomaly detection for data that has been normalized. On the center, I show the results that were obtained with the robust anomaly detector that I showed in the middle of the presentation. And on the right, I show the results with the anomaly detector on the sphere. So remark that the first row, that it has the faintest target, it's not detected by the robust fixed-point anomaly detector. The classical one detect one or two targets, but not all of them. And for the proposed detector, we can see that it manages to detect most of the targets, except for those whose the signature is very, very close to the anomaly, to the current anomaly. So it's important to emphasize that this detector, it's mainly focusing on the difference in the shape of the spectra instead of the energy. So instead of the amount of the brightness of the pixel, it's mostly centered on the shape. So just to conclude, I will explain why this works better and why these target detection methods work better with the M estimators. It's because they're robust, and they're robust to the presence of impulsive samples in the secondary data. They're also robust to heterogeneity. So as you're moving the sliding window through the image, probably at the edges you'll end up having some multimodal distributions. So the M estimators are robust to the fact that you may end up having targets, unexpected targets in your secondary data. That this will strongly deteriorate your estimates, and targets that are larger than 1 pixel in the cell resolution. So usually what it's commonly done is use some guard windows, some guard pixels around the center. But this guard pixel won't be enough. It won't solve all these problems. So that's why M estimators are robust and to the presence of strong scatters and impulsive samples. So just to conclude, I presented the fact that hyperspectral images, as well as is also the case for radar or SAR images, they can suffer for non-Gaussianity or heterogeneity, and this fact can strongly deteriorate the performance of detection for both anomaly detection and target detection. That's why the class of elliptical distributions is very useful to model the hyperspectral background of the image. This can match and overcome this heterogeneity. Also, jointly use the robust estimates with the proposed detectors. What we can say is that they provide a better performance and better false alarm regulation. The case is that if you actually have Gaussian distributions and you've assumed that your data is elliptical, so the performance will be almost the same as the Gaussian case. the loss in performance, it's very small compared to the Gaussian detectors. Moreover, I want to point that compound Gaussian models that are a subclass of these elliptical distributions and robust estimators have already been considered for calibration tasks in radioastronomy in the work of Eugénie Ollier in 2018 in her PhD. And I think the one interesting perspective of this work could include source detection or even transient detection for radioastronomy. Thank you for your attention.
Thank you very much. So, questions? Yes, David.
Yes, hello. I was very interested in the way you're detecting the anomalies with the different spectral shapes. Could you go back to slide 32? Because I would like to understand exactly what you're doing. Because in principle, you assume a prior shape for the spectra, right? And then you decide that there will be differences. So how do you quantify the differences with respect to your prior spectra?
So what we assume is that our underlying hyperspectral data is elliptical. And then by projecting to the hypersphere, we get rid of how impulsive the data is.
Right, but you mentioned
our prior is on the, yeah, sorry?
No, sorry, go on.
So our prior is mainly on the model, that this is elliptical, our data is elliptical, and then when we normalize it, the generating biorate won't intervene anymore.
Yes, no, that's fine. But if you go back to slide 32, you're saying that, yeah. Right, your detector of anomalies depends on the differences in the shapes of the spectra. Right, so you have some target spectrum, right? And you're saying you are going to assume some differences with respect to your prior spectrum, and then use that as information to actually for the detector. And that would be extremely interesting for many other applications in astronomy. So I would like to understand how you actually put a prior on the differences in the shapes.
Okay, so here what we use is an angle detector.
Okay, sorry.
At the end, it's like it's an angle detector.
It's an angle.
By normalizing everything.
So it does not depend on the wavelength or frequency.
You have to have the, so in the image, yeah, definitely depends on the values of on the different wavelengths. You need to have at some wavelengths that the spectra being different enough to be considered as an anomaly.
Exactly. So that was my difference. How different should they be?
It depends on how, I would say that it depends on how many bands you have. Because if it's different enough on a part of the spectrum, only on a certain wavelength, it should be enough.
Okay, so it will be enough, say, in one of the frequency bands, so you have a difference, and that will be enough.
It depends on how many bands. If it's 1 out of 5, maybe yes. If it's 1 out of 200, no.
All right, excellent, excellent, yeah.
Thank you.
So perhaps I will contact you offline so we can continue discussing.
Okay, thanks.
Yeah.
I had a question. At some point you said that you detect anomalies, but you cannot distinguish if it's bad pixels or signal. I was looking at the example you gave for the Muse cube in your paper, and so is it correct that you that you cannot distinguish the two?
Yeah, in the Muse example, I had no idea what I was looking for. so it's the same thing I showed here in the last slides. I just search to detect anything from the surroundings. So what we observed is that using this 6 point, most of the heterogeneity on the image was strongly reduced, but we don't know what are the bright points in the image.
Okay. Okay, very nice.
Yeah, I have another question, if I may. So the reason why you're using elliptical distributions is just for computational ease, because I can imagine many other distributions which will have heavier tails and perhaps are better for the data.
So we chose to use elliptical distributions because as it wasn't Gaussian, so we thought that the data were in Gaussian, but sometimes they could be Gaussian. So we wanted something more general. So that's the main reason why we started using the elliptical distributions.
All right.
Because Gaussian wasn't enough, so we wanted to be more general and not only heavy-tailed.
All right, thank you.
Thanks.
How fast is the computation for given Q? Do you know?
It's quite fast. Like one of the, I don't have an order of magnitude. It mainly depends on how big your sliding window is, but it's in terms of I don't know, seconds. It's not it's not slow.
Okay.
It just yeah, just 2 multiplications. It's not very heavy.
Any other questions for Joana? No, so thank you again. Thank you everybody for attending this seminar, and see you for the next seminar.
Thank you. Bye.
C'est bon, David, pour toi?